on behalf of Berkeley Public Library, I want to thank everyone for tuning in tonight. Our library is just so delighted with our partnership with Popping the Science Bubble. Popping the Science Bubble is a monthly science lecture that happens on every third Tuesday of the month. And the science lecture is a partnership with UC Berkeley, where we bring in students from Cal, postdocs, graduate students who talk about their science research or a science topic that interests them. And the program is run by three fabulous graduate and postdoc students, Oksana, Madison, and Jenna. And if you want to see more Popping the Science Bubble events, you can visit the library's YouTube page. You can also visit Popping the Science Bubble's WordPress website. They're also on Twitter and they're on Facebook. And I will hand it over to tonight's host to introduce tonight's speakers. Thank you.
Thank you, Kelsey, for the great introduction. I also want to start by encouraging everyone to ask questions during the course of the talks. And you can do this using the Zoom Q&A function. And you can also leave comments on the Facebook live stream. We will be monitoring both to ask the questions during the talks. So for our first speaker tonight, that is Syamantak Roy. He grew up in Calcutta, an eastern city in India known as the City of Joy, and also a city which has bred 4 out of the 6 Nobel laureates from India. He would have ended up playing professional soccer in India had it not been for the academic environment of the city, which led him to grow a keen interest in chemistry, culminating in a PhD. He is currently a postdoc in the chemistry department at UC Berkeley, working in the group of Professor Jeffrey Long. His research involves the development of materials that selectively capture carbon dioxide over other gases from point sources of emission. When he is not in the lab, you would probably find him playing or watching soccer, and he is also occasionally a singer and enjoys running. Take it away.
Perfect. So I'm going to go ahead and share my screen. It should be visible now. Right. Yeah, great. So thank you, Oksana, for the wonderful introduction. And so today my topic is just to make you aware of the perils of rising CO2 levels in the atmosphere and what approaches we are actually taking in lab to mitigate that. So the talk tonight would address 2 questions. One is how climate change is actually affecting us. And second, what are we actually doing about it? And if you're thinking that we could plant more trees and just get rid of carbon dioxide from the atmosphere, we're just not doing that. In fact, we're not also turning vegetarian, right? So we need to look at chemical compounds which can capture carbon dioxide from air and then reduce the level. Now let's get straight to the point. The curve that you see here shows you an exponential rise in carbon dioxide levels over the past century. Now, if you see dating back to the past 800,000 years, the level has not risen above 300, but then starting 1950, it has risen to a level of 420 ppm right now. And this actually coincides with the Industrial Revolution that has happened and with all the technology advances that have been going on. This is just not a coincidence that with human growth, the carbon dioxide levels are increasing. Now, if we zoom into the last 20 years, you see a linear progression here, and there's almost an average of close to 15 ppm increase per decade. Now, what is leading to this sudden CO2 uptake, and what are the effects of it? Now, the first effect, which immediately comes to one's minds, is basically global warming. Now, what happens when carbon dioxide, being a greenhouse gas, which gets trapped in the atmosphere, it just leads to a hotter world. Now, once that happens and the temperature of the Earth increases, it leads to widespread catastrophes like glacier melts and rising sea levels. But there are a few things which are actually going unnoticed. So the first of that is actually loss of marine life. Now, what do I mean by this? So once the Earth gets hotter, the level of dissolution of CO2 into the oceans actually increases. And once CO2 goes into the oceans, the pH, or the metric by which we actually consider the acidity of a particular system, goes down. Now, there is a formation of carbonic acid in the oceans, which keeps on increasing with increasing CO2 levels. And this actually dissolves the protective shells of crustaceans. Now, once this happens, slowly they lose their shells and it leads to the disappearance of marine life. Now, you'll be thinking that, this is just one particular species which is getting affected by this, but then this has a domino effect on the entire ecosystem. So this is one problem. And the second more severe problem is the impact on humans. Not only does it lead to flooding in different cities due to rise in the CO2 levels in the atmosphere, it could also lead to weather catastrophes, disease spread, and also malnutrition in developing countries. Now, this happens because under high CO2 levels in the atmosphere, a lot of plants have stunted growth. They lose a lot of nutrients, and is irrespective of the fact whether you're a vegetarian or a non-vegetarian, this could actually lead to malnutrition, and especially in developing countries where the access to food is not that great. Now, there was a slight ray of hope when everything went under lockdown in March, and people thought that, due to human inactivity, there would be a decrease in the CO2 levels in the atmosphere. But we should take lessons from history, which shows us that, after every recession, the CO2 level always climbs back, as you can see on the chart on the left. And indeed, the Global Monitoring Laboratory, when they flew a plane with an IR radar over the eastern part of the US, they did see that the levels are kind of the same that was there pre-lockdown times. Now, what actually leads to the high CO2 levels? Now, if you look into the chart on the left, you see that CO2 is actually the principal culprit for all global greenhouse emissions. Now, as you can see, 65% of carbon dioxide is actually emitted into the atmosphere due to the burning of fossil fuels and also a lot of other industrial processes. Now, as I mentioned here, carbon dioxide actually makes up close to 80% of the emissions which are there due to the industrial processes. Again, if we look into the red part of the curve here, it's basically the power generation plants, not across the US, but also throughout the entire world, which leads to massive or copious amounts of CO2 being generated into the air. Now, before I go into the details of how we can actually mitigate these CO2 levels in the atmosphere, we should try to understand how we can actually devise a technology which can capture carbon dioxide from point sources. And what I mean by point sources are these factories and chimneys which let out flue gas with a high concentration of CO2. So the usual process of any power generation, be it in a coal plant or a natural gas plant, involves the burning of the particular fuel in air. Now, once you burn the fuel, you generate power. But then again, it actually leads to the release of a gas mixture, which is predominantly CO2. Now, this is where we scientists actually come in. If we could actually devise a technology which could selectively separate the CO2 from the other non-greenhouse emittive gases, then we could have a pure CO2 stream, which could either be used for chemical transformations into value-added products, or could actually be geologically sequestered within the earth. Now, in order to devise such a technology or a system which could selectively capture the CO2 over the other gases, we need to meet certain criteria. And the first of that is that the material which would separate the CO2 needs to have a high capacity and also a high selectivity for CO2 over the other gases. And also it has to be robust under multiple cycles of this separation technology. Now, the technology that I'm showing here dates back to like the 1930s, where if you use this compound, which is known as an alkanolamine, and you react it with CO2, this forms a chemical species called the carbamate. Now, the process which goes in actually capturing the CO2 is basically where you flow in the flue gas through the adsorber, which is the alkanolamine here, and then you selectively capture the CO2 and let out a CO2 lean flue gas. Now, once all the CO2 is captured here, the CO2-rich amine is actually put through a desorber bed, which then dissolves the CO2, and then we can use it for other chemical transformations or even sequester it. And then once the amine is stripped of the CO2, it goes back to the adsorber bed. And again, the second cycle of the CO2 capture begins. Now, I won't go into too much details of the mechanism of this capture, but the one thing I want to point out here is this chemical species called carbamate, which I'm going to be using a lot in further discussions. So what happens is that these are electron pairs on the nitrogen atom. This acts actually as a nucleophile to react with the CO2 and initially form a local carbamate. And then this carbamate abstracts a hydrogen from a neighboring alkylamine to form this carbamate pair. This can also go through a concerted mechanism. And once you start heating this particular carbamate pair, the CO2 gets released and the amine is generated back, and then more CO2 can come in and react with the alkylamine. So what are the drawbacks of this technology? If you remember, I said this is probably an outdated technology. It's been used since like the 1920s. The first reason is that these amine solutions are highly corrosive. So the vessel in which they are contained in, they kind of degrade the vessel over a period of 1 week. So we need to regenerate the containers and use fresh containers to store these amines. The second problem is the low working capacity. So what I mean by a low working capacity is that the amount of CO2 that can react with these alkylamines are pretty low. So if I give you a kind of number where one alkylamine reacts with one CO2, that's not always the case, and it ends up reacting with maybe 0.4 molecules, and hence the amount of CO2 that you can capture using this technology decreases. The third problem is that, as I mentioned before, the flue gas stream contains a lot of oxygen, and this oxygen actually oxidizes the alkylamine in solution, and therefore these degrade over time as well. And also, a high temperature is required to actually regenerate these alkylamine solutions which have already reacted with CO2. So you see that we don't have a better technology, and that is the reason why we are still using this alkylamine solution in an industrial setup. This is primarily the reason why we need a solid adsorbent. Now, what do I mean by a solid adsorbent? A solid adsorbent would be one where these are porous like a sponge, and CO2 would just come in and sit within the pores. And then just by using low grade heat or even lower temperatures, you could get rid of the CO2 and regenerate the materials again. And these kind of materials, which are known as metal organic frameworks, which I've abbreviated as MOFs here, have high working capacity. They also require low regeneration temperature. But the drawback for these materials is since these are the CO2 has to react in an aqueous environment, this has poor capture capability in presence of water. But then again, I think the positives actually outweigh the negatives, and hence probably a MOF with an amine inside the pore is a probable solution. Now, before I go into the details of MOFs, let's understand how a solid adsorbent would work. So here you see a column which is packed with the MOF or the metal organic framework structure, which I showed in the previous slide. Now you pack this in a highly dense manner, and then you flow in the flue gas. Now, at the initial stages, the material would selectively start capturing the CO2, but let out nitrogen gas. Now, as the time of the flow increases, the adsorption bed would finally get saturated with CO2 at the same time releasing nitrogen. And this is the point where we stop the flow and start heating the adsorbent bed and release the CO2. And it goes back to its initial phase where it can again go via the next cycle to capture more CO2. And ideally, this should last for at least 10,000 cycles, which is not possible for the alkylamine solutions that I discussed before. So let's get into the chemistry of metal organic frameworks. So these are highly porous crystalline systems and composed of a highly ordered chain of metal ions at the nodes here and an organic linker. Now, once these self-assemble to form the porous structures, these actually pack into a high surface area within a gram of the material. Now, just to give you a perspective of how high the surface area is, the surface areas can go up to like 7,000 meters per gram, and that would actually fit in a soccer field within 1 gram of the material. Now, you can totally imagine that if 1 gram of the material has such high surface area, when you're packing the adsorbent bed with kilograms of these porous structures, you can actually capture a lot of CO2. Now, if I zoom out of the chemical diagram of a MOF that I've shown here, you would probably see these kind of crystals under the microscope. So these are like a repetition of these pores packed within this crystal. And if you zoom out even further in the naked eye, it actually looks like this. This is a 30 milligram material, which can actually capture close to 3 millimoles of CO2 per gram. Now, we're looking at technologies in our lab where, we can capture more and more of CO2 using as less of the material as possible. Now, the capture target that is set by the Department of Energy in the US is that we have to achieve a 90% capture of CO2 from the point sources and also at a high working capacity over multiple cycles. So we're looking at ways in which we can tune the MOF structures here in order to increase the amount of CO2 uptake in these frameworks and also have a high cycling capacity. Now, the material that we use in our lab here is composed of the magnesium metal ion, which actually reacts with this organic linker. So what I mean by a linker is that these organic moieties will actually react with magnesium to form these ordered porous structures. And here, the magnesium ions are actually shown in green, whereas the gray depicts the organic linker. The fascinating thing about this particular structure is that these have open magnesium sites. And what I mean by open sites is that these are reactive sites on the metal ion where we could do some more chemistry in order to increase the carbon dioxide capture. So this is a zoom in of the chemical environment around the metal ion. As you can see that it is bonded to 5 oxygen atoms here, leaving one of the sites free for any diamine to come in and bind. And that is exactly what we do. After synthesizing the MOF here, we bind it with the diamine structures so that we can have a high capacity of CO2 interacting at all these amine sites. Another interesting thing is the mechanism here. So this is a schematic showing how the amine-appended metal organic framework actually reacts with CO2. So one molecule of CO2 actually comes in and interacts to form a local carbamate here, if you remember the carbamate species that I discussed before. Now, once this happens, there occurs an ion pairing, and this interaction destabilizes the next event spot here. Now, the second molecule of CO2 comes in and then reacts, and this actually goes on until a complete 1D chain of ammonium carbamates are formed. Now, these are held by weak interactions, so you don't need to go to like really high temperatures to get rid of the CO2 from it and regenerate the diamines again. So this is how a usual CO2 uptake profile for the metal organic framework looks like. So this is the phase where we have the carbon dioxide coming in and reacting with the amine. So initially you wouldn't have a high uptake, but once the 1D chain formation happens, you get a sudden jump, which leads to a very high amount of uptake within a short period of time, and then it levels off. And why is this kind of a sigmoidal curve important industrially? So for that, we need to look at the curve that is generated for the traditional alkanolamine solutions. So if I just quickly go through the curve on the left, this is for a traditional adsorbent where at a very low pressure, a high amount of CO2 is absorbed. But if you are working at a higher temperature, which is required to get rid of the CO2 or regenerate the material, it still captures a significant amount of CO2. So you can't just get rid of the entire CO2 by increasing the temperature to a high degree. But when you have a sigmoidal curve, when you decrease the pressure, or increase the pressure or increase the temperature as well, the curve just shifts to the right. And as you can see, even at high temperatures, it has minimal uptake of the CO2 gas. Now, once this happens, you can also get rid of the CO2 or regenerate the material at even medium temperatures. So not only do you have high CO2 absorption capabilities in this sort of a curve, you actually induce high working capacities, and also you need a lower temperature for regeneration.
Hi, so we have a question. So we have questions saying, can the MOFs be mass produced?
It can be, yeah. I don't want to divulge the details, but we are already in collaboration with a lot of gas companies and also startups which have been doing it in pilot plants, and those seem to be working. So, the next step is actually using them in an industrial setting. Just to give you a perspective, we can actually make like tons of these MOFs, and that would take maybe 2 weeks for the synthesis. And I think that's a short window within which we can actually get the MOFs ready for an industrial application oriented work. Right. I hope that answered your question.
I don't see any follow-up, so I think so. Yep, thank you.
Cool. Right. As I mentioned before, there can be different point sources at which we can capture the carbon dioxide molecule. One source is the coal flue gas. This is the flue gas which comes out when we start burning coal. And usually the percentage of CO2 mixed in other gases is about 15%. So we need to have a capture target of CO2 within 150 millibars. And in order to meet the DOE targets, we need, that is like greater than 90% capture of the CO2 from the stream. We need the material to be operating at 40 degrees C and at 15 millibar pressures. Now, when we go to natural gas, it becomes all the more harder because the percentage of CO2 in a natural gas flue gas is as low as 40 millibars. So we need to be capturing the same amount of CO2 at 4 millibars. And also, when we are talking about direct air capture, which I kind of bypassed in today's talk because it's a lot more complicated where, in addition to any separation technology or separation material, you also need a lot of turbines to suck in air from the atmosphere. And if you go back to school lessons, the percentage of CO2 is less than 3%, and therefore we have to be capturing CO2 from air at like ultra low pressures of 0.03 millibars. And this is a topic which a lot of scientists are pursuing right now, because if we do not have a good direct air capture technology, we're never going to bring it down to the levels which we had before 1950. So in our lab, we're actually trying to address all these three issues. Now, interestingly, the structural tunability of the MOFs that I showed you before can be done by varying the metal ion or the diamine structures. And I don't want to go into the details, but we've seen that by varying the metal ion from magnesium to iron, even copper, we could tune the step temperature of the CO2 capture. And also by tuning the structure of the diamine, we could actually have a system which falls within the window of each of these targets. This is one such example which we've achieved so far, where by growing crystals, we've been able to prove that the diamines actually capture CO2 by forming the carbamate chain that you see here. And this is the 1D chain that I showed you in the schematic in previous slides. And along with the carbamate chain, we also have carbamic acid pairs forming. So in one direction, the chain formation happens, and in the other direction, the compound is stabilized. So we have a lot of CO2 going into our system. And since these are weak hydrogen bonds, we could break them easily to regenerate it within the window which the DOE has set us. Now, interesting thing about this plot is that if we go slightly left, we can actually get more than 99% capture, but then we actually have to shoot up the temperature to close to 200 to regenerate the material. So we'll have a lot of loss in, gaining that energy to increase the temperature. And if we go to the extreme right of this plot, we see that we can shoot down the temperature to as low as 75 degrees, but then we compromise on the percentage of CO2 that goes in. So this particular material is working within the window, and we're trying to scale up this technology in order to have a more than 90% capture with minimum regeneration energy from coal flue gas. And with that, I want to thank my mentor, Professor Long, who has given me the freedom to try different ideas on how to tune the step temperature and the pressure in order to have an industrially important compound. And also the people mentioned here, we are a part of Team CO2. So we look at different aspects of MOF tunability so that we have a material which can be translated to the industry, and also the long group members who've actually created a great atmosphere so that you can work freely in lab. And also I should not forget mentioning the Fulbright program, because the scholarship helps me pay my bills and stay in Berkeley, and also Popping the Science Bubble team and the Berkeley Public Library for hosting us. And I'll be happy to answer questions.
Okay, great. We do have a question from one of our Zoom audience members. What is there to do with all the carbon dioxide once it's captured?
Oh yeah, so there can be a lot of possibilities that you can do with that. There are other research groups, not only in Berkeley, but around the world, which are looking at technologies where you can use the pure CO2 stream to convert that into methanol, which is a value-added product. It can also be used to generate carbon monoxide, which is again a starting material to produce hydrogen, which is a cleaner energy alternative. The other way is actually looking at pumping the CO2 down to the depths of the earth, and this is called geological sequestration. And the places where this is being done is basically depleted oil wells, which can't be used anymore. So we just pump it down deep within the earth and store it there and make sure it doesn't leak out.
So if I can follow that up with my own question, obviously the natural environment is that plants or other flora uptake CO2 to convert it to oxygen and solid carbon skeleton mechanisms.
Yes.
How much research is there being done to try to mimic that biological process in these carbon capture mechanisms?
Yes, it's interesting that you brought this up. This is actually a field in itself where people are trying to mimic natural photosynthetic processes in order to generate chemicals which can do it. The only problem is that the procedures that have been developed so far, where you can just pump in CO2 and release oxygen, are less than 1% efficient. So we've got to do a lot more in order to catch up with nature. But then again, we're still hopeful that at some point of time in the future, we would be able to do that. But yeah, it is indeed possible.
Cool, thank you.
What are the size scales for those natural ones? Because solar panels are pretty low efficiency too, but if you have enough of them, you can still harvest a lot of solar energy. So are they for these tiny, or are these giant chambers if you wanted to have thousands or millions?
Yeah, I think you would probably eat up a lot of earth space if you've got to develop materials which can actually take in all the sunlight and then capture the CO2 at the same time and release oxygen. So we've got to look at uncharted places in the earth where we could actually fit in these systems. And also, yeah, I want to add to that as well. So I get a lot of questions from people that, this is a very simple solution, right? We could just plant more trees instead of spending millions of dollars on developing these materials and putting them in the factories. But the problem is the amount of land use that would be required to plant trees and reduce the carbon dioxide levels is just not worth it. So we need to look at like smaller technologies which would occupy less space, and in spite of occupying the lesser amount of space, would capture more CO2 than trees.
Okay, and we have another question for you. What are the long-term consequences of sequestration?
It's all this is an interesting question. The current technology actually does not allow you to like take it out of the earth and use it, and there are always hazards of leaks of CO2s from the earth. But the good thing is that once you actually sequester these CO2 molecules into the earth, these kind of react with the soil surfaces and get embedded in it. So right now it's a safe technology, but then, with the amount of CO2 that we're releasing into the atmosphere, we would probably soon run out of space and then think, we would have to think about alternative technologies where we could actually store these CO2 molecules.
Seems like storage is always the problem for a lot of science questions here.
Yeah.
Okay. And maybe we'll do one more question before we move on to our next talk. So for our final question, how much carbon dioxide can you imagine being reduced using this process?
You mean like the amount that is being captured or reutilized?
Good question. Maybe we can see how much can be captured. I'm not sure if you want to clarify.
Yeah, I could actually answer both. So if you're looking at the amount that we are actually aiming to capture, if I put it into numbers, it would be at least megatons of CO2 in an industrial setting. So if this industry is running over a long period of time, it would keep on, releasing carbon dioxide. But over a period of maybe a year, megatons could actually be captured using these materials. Now, if you're talking about reducing or reutilizing the carbon dioxide that is being captured, for any catalytic conversion processes for carbon dioxide to value-added products, the number is still low. I do not have exact numbers, but we would always generate more CO2 that we can actually use up.
Okay, great. Awesome. And so if anyone has any more questions, you can always feel free to type your question into the Q&A box. And I realize our speakers can actually type responses back to you. And so feel free to use that option as well. So thank you again, and a virtual applause for this great talk from Syamantak.
Thank you, it was a pleasure.
All right. So now as our next speaker is getting set up, I'll introduce Dillon. Oh, no, lost the introduction. Okay, yes, so Dillon was born in Santa Barbara, California, but moved to a small town near Yosemite National Park in the 6th grade. Dillon returned to Santa Barbara to study electrical engineering and is now a second-year PhD student at UC Berkeley making tiny robots. Dillon has had some health issues last year, which are part of the reason why he's driven to make biomedical devices. In his free time, he likes to play sports, take day trips around the bay, find different food spots, and binge shows with a cozy blanket and some snacks. With that, we'd like to welcome Dillon.
Thank you, Jenna, for that nice introduction. Hi, my name is Dillon, like you said, and I'm going to talk to you about small robots making big changes. And if any time you have questions, please jump in, put it in the Q&A. I think some of these can be really complex topics, but it's good to ask questions to kind of get a better understanding. Like that's why you're here. So first off, I kind of want to just go by and start explaining like how small is small. Well, MEMS is small, and in this case, MEMS is an acronym kind of meaning small robots. To kind of give you an idea of when I say the word small, this is a picture of kind of a standard insulin pump. It's handheld. But this is a MEMS insulin pump. Rather than being handheld, it can easily fit on the tip of your finger. And then to kind of go even smaller than that is three blood pressure sensors on the head of a pin. And to kind of explain this picture, this is not a nail we're looking at. This is the head of a pin, and we can fit three MEMS-based technologies blood pressure sensors on this tiny device. So when I'm talking about the word small, I'm not saying handheld. I'm saying fits on the tip of your finger, or even multiple on the head of a pin, or even smaller than that. And you may be thinking like, well, what amazing materials can this be made out of? A lot of times in the news, they'll use fancy words like nano and ferromagnetic and all that. And the answer is it's sand and glass is really what these materials are generally made out of. Silicon is the second most abundant element in the Earth crust, oxygen being number one. But we can harvest silicon from basically the Earth crust or from sand. And the second, glass, is actually kind of rust. And what I mean by that is, let's say you've left some piece of metal outside and it gets wet, it's exposed to water and oxygen. After a while, it's going to lose its kind of shiny appeal. So if you have some piece of metal, you leave it outside, the metal is still there, but there's some other material that's kind of coated it. That's rust. And that's pretty much what silicon dioxide is. So if we take our material silicon, which we get from sand, and we expose it to oxygen and water, then we're going to get the secondary material, silicon dioxide. So those are the two. One comes from sand and one is basically rusted sand, or that we call glass. And I just pointed to a window up there. And it's like, okay, well, we're not actually using pieces of sand in the lab. What it actually looks like is something like this. And this is a silicon wafer that we start off in the beginning of the lab. It's the thickness of it varies. It can be anywhere from much thinner to the thickness of your hair to a few hair lengths thick. And then the actual size of it varies. They started off about 2 inches and they've progressively getting larger and larger. And the reason for that is the larger it is, the more of these little boxes you can fit on there. And what these little boxes are is they're usually repetitions. So each of these boxes are the same thing. And whether that box is maybe one of the insulin pumps that I showed you that can fit on the tip of your finger, or maybe it's 1 million of the blood pressure sensors I showed you that can fit on the head of a pin. And what is in each box kind of depends on the design and the process. But basically, it's taking a piece of silicon wafer, and we do some kind of magic to it, and we get all of these amazing devices. And where that magic happens is the clean room. And if you ever on the Berkeley campus, you can go by Sudhajadai Hall, and on it's their second and third floor, they have kind of an orange windows room, and you can maybe see people like this, where I've definitely been walking around and I've had lots of tour groups stop and take pictures and point at us. And the reason we're wearing this protective material is not to protect us. Unfortunately, this doesn't really do anything for us in terms of some of the chemicals that we use. The real protection is for the devices that we're making. Because I showed you before, if we can fit 3 blood pressure sensors on the head of a pin, then what's one of your hairs going to do? Or what's one speck of dust going to do? And the answer is it could, depending on the size, it may mess up a little bit, or it could completely destroy one or tens or hundreds or thousands of your devices. So the point of the clean room is to emphasize clean. And what I mean by clean is, we've kind of heard about parts per million in the last talk, is they can count the number of particles, and that's the class of the clean room. So ours is about 100. So there's just, there's maybe 100 kind of particles going around in a cubic kind of foot of air. And that's just how clean it really is. And to kind of explain what goes on in here and what we do, it's called fabrication. And what is fabrication? And I kind of spent some time thinking about a good analogy to describe what this is. And one thing that I came up with is fabrication is basically like baking a cake. And kind of stay with me here on the analogy. So in baking a cake, you have the top of the cake here, where it has, in this case, it has different raspberries and different dollops of frosting. But if we cut into the cake, and then we can see inside on the side here, we can see different layers of cake and frosting. And we can also see, the side or the cross-sectional view of these dollops of frosting or these raspberries. And that's basically what we're doing in the clean room. So we spend tens or hundreds of $1,000,000 on these extra clean places. And essentially what we're doing is we're baking cakes, but just very small cakes made out of glass and sand, like I said earlier. And what this kind of looks like is something like this. And to kind of explain what this image is this is a super zoomed in photo where this is the top view. So this is like the top of the cake here. And then this section here is where we've cut it. So this is looking at like the side view of the cake. And to kind of explain what's going on here, so there's really three main steps. Is the first is there's deposition. So we start off with a layer of cake that we can kind of see down here, and then we would put a layer of frosting on top of it. But we don't necessarily want a whole layer of frosting. We want to have, some different holes in here where we have frosting here, but then cake, and then frosting again, and then cake, and then frosting again. And how we actually do that on this such small scales is we actually use light. We can use lasers to basically control where things stay and where things get removed. And that's kind of the third step, is the actual removal process. So the first step is the deposition, where we can lay the frosting down or another layer of cake. The second step is we use light to kind of pattern to decide, I want to keep frosting here, and then I want to remove the cake here. And then the third step is the actual removal or the etching process. And so if you understand that, that's basically all there is to fabrication. It's a little bit more complicated, but that's the basics. And you can kind of join us in the clean room and help us bake some really small cakes. So what you can actually make with this, other than kind of the two pictures I showed you in the beginning, some really cool structures, I think. We like to have some fun in the lab. These two pictures are from a talk my professor, Chris Peaster, gave a while back. So this is actually a very small scale H2 Hummer. And to give you an idea of how small this is 240 microns long, and the average human hair is roughly about 100 microns thick. So this is 2.5 thicknesses of hair length long. That's how small this is. Which is kind of cool. They wanted to make a Hummer, but I also think you can make some really beautiful structures too. I think this butterfly is really awesome. But the important thing about these structures is not just how small we can make them, is what they can actually do. So these two are stationary structures, but we can also make some movable structures. So here we can see some images of a walking robot. So here is just a zoomed in photo of one leg, basically actuating, where it'll come up, it'll step down, and then it'll swing across, and then it'll reset, and then take another step. And then here we can kind of see those legs in action. There are 3 different legs. So this image zoomed in here, we see 1, 2, 3 legs, but only one is actually going at this point. We kind of wanted to see if this robot could walk with only 2 of its legs. This is symmetric on the other side. So it has 6 legs. We're only using 2 of them. We just wanted to see if it worked. And as you can see, they're slow, they're not very big, but it is taking steps. And this was a really big deal of, making these micro robots that can just slowly start to walk around. It's like, well, okay, awesome. We can make a walking robot. It'd be really nice if we could pick stuff up too. So we made a gripper. And this is the MEMS component right here. Again, MEMS just meaning small robot. The rest of this is just a stage to help us move it around. And we can see here is this basically little arm is closing in on the leg of this capacitor. And once it closes, we can actually lift it up. And now we can walk around, and now we can pick stuff up. And this is going to be an interactive kind of portion. This is some structure that we've made in the lab, and I want some people to kind of guess what this structure is. So put it in the chat, put it in the Q&A. What do you think this structure does? I kind of want to get an idea of what people may think. Any guesses? Other panelists maybe want to guess too. Okay, we got a couple coming in. It's not pulling up. If one of the panelists could just read me what the guesses were, the chat's not coming up for me.
We have a couple guesses for solar panel. Solar
panels, cool.
Someone says pipetting.
Pipetting.
Super, super small pipetting. Maybe cuts or a leveler. Okay.
Awesome. I love, those are all good guesses. Those would all be great. I'm actually working on a solar panel design right now. That's actually not what this does. Here's a video of what this robot actually does. It can fly. So we can make in the clean room, and the point of doing it in the clean room is it's these high volume processes where if you can make one, it's really, really easy to make millions. And so now showing that this can fly, again, it's a little wobbly, but that's kind of the first step that we're taking. We could just have swarms of these little flying robots, which is a lot of cool applications coming to that. So like, cool, I showed you walking, I showed you gripping, and now I've shown you flying. We also have jumping. So no video this time, but we can kind of see the different pictures of this robot as it's jumping. So this is as it's, you know, coiled, it's right about ready to jump. This is as it starts to go up, but right before it jumps off the ground, and this is at the height of its peak. And these line spacings are about 1 millimeter apart. So maybe thinking, okay, well, this, like, cool, it jumped a couple millimeters. And my response to that is, one, you got to start somewhere. We're not going to be making robots that, you know, are jumping all over the place right off the bat. We got to start somewhere. And this is, as far as I know, this is the record height jump for a robot of its size. And it's cool because other robots will base or use kind of chemical combustion to make a small explosion to shoot it up. This is actually repeatable, where it can jump over and over again. And the second thing has to do with gravity. So gravity, as you probably know, is an attractional force between two objects, and it depends on the size and the mass of said object. So the gravity on Earth is a larger force than the gravity on the moon because the Earth is larger than the moon. So if we took these jumping robots and put them on the moon, they'd be able to jump a lot higher than the 2 millimeters that they can only jump on Earth. And the idea of this, and we're sent a proposal into NASA, is, well, what if we had thousands of these little jumpers, and instead of them sending, you know, 1 or 2 really big, really expensive probes to circle some other asteroid or some other planet, what if we just let loose 1,000 of these little jumpers, and they could hop all around, and, you know, because there's a lot less gravity, they can jump much higher, and it's a lot easier for them to move around there than it is on Earth. They can get, and if they're armed with a different sensor suite, they can collect all this data, and it's a lot cheaper, and it's a lot lighter, and it's a lot more reliable, because if a couple of these break, that's fine. You have thousands or potentially millions. But if you send one really expensive probe, if that breaks, you're in trouble because you can't get any data out of a broken probe. So that's one cool idea coming on here. On the next, this one is near and dear to my heart because it's one that I'm working on.
Hey, Dillon, we do have one question about the jumpers.
Yeah, awesome.
It's, how does this jumper jump? Is it a spring-like mechanism, since you mentioned that other jumpers use chemical combustion processes?
Yeah, awesome question. That's exactly what it is. So if we can see here, sorry, I have a more zoomed in photo, but these rovings kind of going side to side where my mouse is moving, that's a stretched spring. So this is the springs fully stretched. And then this image is, we've let go of the spring, and this is right before it's taken off. So this is the springs are fully stretched, and this is the springs are fully compressed. So this is kind of the point where it's turning all that potential energy into kinetic energy. And then this is again, the point where it's used up all that kinetic energy that it's stored in the spring. But yeah, awesome question. And the way that we store energy in the spring is we have, we essentially just move, we just move. Actually, I don't want to get too much into it. Yeah, we store the energy in the spring, and that's why this is a repeatable jumper.
Thanks.
So the next is, this is a micro silicon poker. Micro just means small. Silicon, I brought up before, it's, you know, that super common material. It's the reason Silicon Valley has its name is because of this material, silicon, and because of silicon oxide. And then poker, you may have guessed what this application is, but just kind of give you a size scale. Again, easily fits, you know, on the tip of your finger. But this pokes. So this blue region here, hard to believe, but it's actually someone's finger. And so this is the edge of said finger. And then this kind of white area over here is the chip that I showed in the last image. And what we can see here is we have this actuation of these really small parts. And again, really small is, this is, you know, 2.5 hair lengths wide here and about 1/2 a hair length into your computer screen. And it's coming in contact with a human finger and then resetting. And then it's able to be used over and over again because it stores its energy in its springs, 2 of which you can see right here. So this may give you a better idea of how the jumping robot stores its energy. It's the same idea. It's like, and this is a fairly simple robot. All we're doing is we're just having it poke, but the applications that come from this are pretty awesome, I think. And kind of the first being virtual reality simulators. You may have this on your Christmas list or Hanukkah list. You may have bought this for someone, or you may never heard of it. Really, virtual reality simulators is you kind of put on this headset that we can see here, and that's your visual stimulation. So it looks like you're in some other environment. You can also have headphones for an audio stimulation, so it sounds like you're in another environment. But what all the systems really lack at this point is that tactile stimulation. The more senses you can kind of trick to think you're somewhere else, the more immersive the experience is. So with these pokers that I showed in kind of the last two slides, if you had an array of them, maybe over your hand or over the back of your neck, if you had the visual and audio stimulation of your flying, you can also have these poke, and we've done some really cool haptic surveys and experiments where some people said, depending on the force, it felt like wind was blowing over them. It would not only look and sound like you're flying, it would actually feel like you're flying. So this is a really cool virtual reality kind of stimulators application. Next would be a Braille cap, and Braille being a language in bumps used for people who are unable to see. So instead of moving your hand across a page, you can have a cap that goes over it, and then you can have your phone or computer or your friend's phone basically send a message to this cap, and it can then use a series of these 6 stimulators to then transcribe whatever it is they're saying or writing, instead of moving your hand over a page. Another one would be tactile feedback for prosthetics, where we can, we've come a long way. You can make really amazing prosthetics for people, but we don't really have that tactile feedback that's really helpful for us to navigate in the world. But with these, we can, add wherever, you're picking up a water bottle, you can have that tactile feedback maybe somewhere else on your body to kind of help you regain a sense of mobility in the world. And then finally I don't know if any of you have ever been bit by a mosquito. I have, not fun. But you don't really feel it, right? Where sometimes you feel it, sometimes you realize later it's like, I got bit by a lot of mosquitoes, like I didn't feel it. But like what's actually going on there is the mosquito's taking your blood, and you may not feel it, which is annoying. But contrasting that is, I personally really don't like needles. So when I go to the doctor and I have to get blood drawn, I'm not happy about it. But if we can draw blood like mosquitoes, it's going to help people like me be more inclined to go to the doctor to get our blood drawn. And that's another idea for this, is a painless blood draw. There's been some really cool research into saying, like, how small can we get the needles to extract the blood is really going to change how painful that's going to be. And this also kind of goes into drug delivery. Maybe we can deliver drugs in this way too. And there's really amazing medical applications that kind of come out of this. And so really, just to kind of summarize everything, these small robots can make really big changes. The automotive industry, huge, whether that's just being safer cars, or going into self-driving. A lot of this MEMS or small robot applications going to that. Space is exactly what I talked about before, with these jumping robots going all over. Agriculture, there's a lot of applications there where that's going to help with pest control or other applications. 5G, just better signals, better networks. A lot of these MEMS technologies are going into helping our infrastructures. Smartphones, if you've ever used maps and you've turned your phone, and then your phone has the little blue arrow and or the lines, and it knows that you've turned, that's due to one of these, something from this technology, is it knows when you've turned because it has a gyroscope built in it. And finally, medical, like I said, even just with this, very basically with the poker, you can have less painful or even painless blood draws. Again, that's pretty basic thing. All it's doing is poking. So if we really get into it, the medical applications are huge. And that's something I'm going to try to focus on in my research, is to help make people's lives better by making these small robots and making these big changes in the medical community. Thank you for your time. Please ask questions. Thanks.
Awesome. Thanks for the great talk, Dillon, and for all the great visuals too. It was really cool to see the MEMS in action. So we have a question here. What do you think were a couple of advances recently that allowed nanotechnology to be possible compared to 40 years ago?
Yeah, that's a great question. and the nanotechnology, just so everyone's on the same page, nano is basically just you kind of reviewing your roots, is it's 1/1000th of a meter. So essentially it just means very, very small, smaller than the kind of robots that I was showing you before. These were more on the millimeter or micrometer, which are 1,000 or 1,000,000 times larger than a nanometer. But the advancements that helped make nanometer scale advancement possible is the kind of is really this huge industry, like companies like Intel and Apple's doing it, is they have their own foundries, they have their own clean rooms, where one huge thing is the lithography step. So kind of going back in my presentation to the fabrication slide where I talked about cake, it's making these, it's how small can you make this line, whether it be twice as big or half as small or 1,000,000 times as small. It depends on that lithography step. And that's using these, they used to just use light bulbs, and now they're kind of getting into using lasers, just because lasers are a much more concentrated form of light. And the smaller we can get, the smaller technology we can make. And that's really, I think, the main driving force. And the idea is, if you've heard it before, it's called Moore's Law. It's how, in the basic principle of it, and it's one of the reasons why laptops have stayed roughly the same price for the last few years. It's because it's the same price, even though that they're getting better. It's because you can fit more into a smaller space, and that's due to kind of this lithography. So I think lithography is the main thing, where if you can kind of figure out more tricks to, oh, instead of making it, this big, I can make it this big, that's huge. And you can then have a lot more applications going into that. It's a great question.
Great, thanks. This person says thank you.
Awesome, cool. Any other questions?
So I have a general one for myself.
Yeah.
There's also someone who, I'll ask the audience members question first. What's the mechanism that lets the flying MEMS fly?
Yeah, that's a great question. And I'm trying to think of the best. It's so this flying MEMS device, it's called the Ionocraft because it uses ions to fly. I'm trying to think of good analogies. And really, let me think about this. What it does is it creates a large potential across a base. It creates a large potential, and what that does is it accelerates these ions being positive particles, down with a lot of force. And what that's doing is that force, those ions are then hitting the molecules in the air, which is then causing a repulse. Like basic physics is, if I hit the table pushes back the same amount. So if you're shooting these ions down, there's a force that's going up. So what this is really doing is it's shooting ions down, which is then propelling this small craft up. And it's able to do this because it's made out of at a small scale, it's so thin, that it's light enough that that thrust from these ions is enough to actually lift it. I know that wasn't the best explanation, but I'm trying to just figure out the best way to kind of describe this without going super in depth in physics. If you Google Professor Pister,
is it kind of like static electricity? Someone asked.
It's not. It's a little bit of a different idea. If you're interested in this, feel free to reach out to me by email, or if you Google Professor Pister, Pister, and Ionocraft, you'll have a couple papers come up, and it'll go deeper into the physics. But feel free to reach out to me as well. I think my email will be provided by popping the science bubble, just because I don't want to. My grandma's on this call, and I don't want to scare her with too much physics.
No, but that's cool. Yeah, we can, I think, get the general idea that like you're using ions to push down and then equal force. I think I remember that from physics. Yeah. So I guess I've heard that silicon is kind of a rare, or is increasingly becoming a rare material just because of our increased usage of it. Is that an actual problem in the near future? Like, are there also ideas for using different types of material other than silicon?
Yeah, so I hadn't heard it hasn't hit us yet that like if silicon's becoming more rare, it's really common. So there's a lot more out there. It's just getting to it maybe becoming more difficult. I'm not super versed in that. But as far as using other materials, yeah, it's huge. When I was down at Santa Barbara, they actually used very few people actually used silicon. Some people use silicon. A lot of other people use different materials. And the reason why you would want to use these other materials and maybe not. The reason to use other materials is there's different cool properties. Maybe the density is a lot lower. So if you want to make this ionocraft, you can make it the same size, but it could be a thousandth of the weight, which means it's able to fly a lot more with the same energy you're putting into it. Maybe it has it's a lot easier for it to accept basically energy from the sun. So you want to make solar cells out of it. There's a long list of reasons why you would. The reasons you wouldn't, one being silicon is just what people have been using. And I know that's not the best reason. It's really tradition is a large reason. But everything is set up to where we know an insane amount about this one material. And there's an interface between, like I talked about in the beginning, the rust, where if you expose silicon to basically to oxygen and you kind of get this rusted silicon, which is silicon dioxide, that interface of silicon to silicon dioxide is one of the most controlled interfaces that human race has ever done. So going to a different material, you may get a lot of these other benefits, but you don't have that knowledge that you did. So you're going to have to do a lot more steps kind of going along the way. So there's pros and cons to doing it. But in our group, we're really focused on using silicon because if we can figure something out, like making the ionocraft, making something fly, it's really easy and pretty cheap to make thousands or millions. And when I say pretty cheap, making a chip, the size of your fingernail is going to cost much less than $1. Kind of thing, depending on how complex, but much less than $1 for sure. So having millions of them isn't that expensive in terms of research money.
Wow, okay, thank you. All right, let's see, any last questions before we wrap up for tonight? Give it a few seconds. Okay. Well, as Dillon mentioned, if you're on our listserv, we'll be sending out just a follow-up about our speakers along with their information, so you can ask them questions then. And you can also email us at poppingthesciencebubble in case you just have additional questions for our speakers or about the seminar series generally. But yeah, thank you everyone for coming out tonight. And I see a lot of thank yous to our speakers for tonight. So virtual applause again for both. All right. Yeah.
All right, and on behalf of the library, I just want to thank everyone. These were fantastic talks, and just thank you so much for coming. We're going to be back January 19th, I believe,
Yes.
third Tuesday of the month. And yeah, thanks once again. I'm really grateful for the work that you all do, and just some incredible presentations.